These are the slides to accompany Chapter 10 on equilibria. So in Chapter 9 we talked about electrolytes, and we identified that electrolytes are really anything that's going to dissolve in water and form ions. So we focused on things that are forming weak ionic bonds, knowing that we could either have strong electrolytes that ionize completely. The math there is not really too complex. We kind of know what's going on. Or weak electrolytes where we have to worry about equilibrium constants in order to determine how strong the electrolyte is. Well, it turns out that depending on how strong of an electrolyte solution we have, we can actually change the equilibrium constants for those weak electrolytes. So if we add enough salt into water, we can make it more polar, and we can actually make it so it will dissolve different types of things, including stronger ionic bonds, and it can change the way that things will equilibrate back and forth. So in order for us to understand how this works, we introduce a concept called ionic strength. If you look at the different solubility products that are listed on the graph shown, we can see that as we increase the concentration of sodium chloride, essentially increasing the polarity of water, we've drastically changed the solubility product for each of our different reactions that are shown. So we need to introduce the concept of ionic strength to help us to identify some of these factors and control for some of these factors. The equation that we use for ionic strength gives ionic strength as mu equal to 1/2 the sum of all concentrations of ions in solution times each of their charges squared. So for example, if we have sodium chloride, we would say that the concentration of sodium would be equal to the concentration of sodium chloride, and then the charge would be +1 for sodium, and then the charge for chloride would be +1 as well. So an ionic strength for a 1 molar solution of sodium chloride would be 1 molar. We call this effect that as we increase the ionic strength of a solution, we see a change in the solubility products, the salt effect. So let's hone in on this a little bit more so we can work through some calculations. This is our ionic strength equation. If we take 1 molar sodium chloride, we set it so that we have 1 molar sodium times the +1 charge of sodium squared plus 1 molar of chloride times the -1 charge of chloride squared, and then we take 1/2 of that sum to give us 1 molar overall. Hopefully that more or less makes sense. It's a little bit more complicated if we generate a solution of 0.5 molar sodium sulfate, because now when we look at the sodium is actually going to be twice as concentrated. So now instead of 0.5 molar sodium, we actually have 1 molar sodium. There's 2 sodiums for every sulfate, and the charge is 1, so that's squared. But then we add 0.5 molar sulfate, that doesn't get doubled. And then we take the charge on sulfate, which is -2 squared. So we see that with that higher charge, we actually end up with a greater ionic strength. The charge has a much more drastic effect on ionic strength than the concentration. So now we have the idea of ionic strength that tells us what factors are leading to an alteration in solubility products, but we need a practical way of implementing this. And so we introduced the concept of activity coefficients to give us activities of a compound or an ion rather than just the concentrations themselves. So when we use concentrations themselves, sometimes we'll get deviations in the solubility products, but when we use activity, defined by A or alpha, equal to the concentration times an activity coefficient, we can use this coefficient defined as gamma of any analyte. That coefficient can define a ratio of the actual concentration that we have that's going to be functionally available in solution. So for example, if we're looking at the equilibrium between silver chloride and each of its dissolved ions, we would normally designate a solubility product, but if we wanted to use activity coefficients instead, that would actually give us a consistent solubility product. So this is the correct way to do this. we actually get a significant amount of error if we use the molar concentrations rather than the activities in solution. So we take the molar concentration of silver times the activity coefficient of silver, the molar concentration of chloride times the activity of chloride, and that gives us a true solubility product. So functionally, activity is then the concentration that's actually available to react. At low ionic strength, activity coefficients are 1. So generally when we have very low ionic strength, we pretty much just ignore activity coefficients, and that's what you're used to doing. That's what you've learned to do in all of your classes so far. At high activity coefficient, or high ionic strength, activity coefficients increase in ways that are really difficult to predict. Oftentimes our activity coefficients are greater than 1 at very high concentrations, and so we end up having bizarre interactions where things are actually more active and more available than you would expect from their concentration themselves. At a medium ionic strength, activity coefficients are given by this equation that's shown. It's called the Debye-Huckel equation. So there are a few things to note in this equation. One is that we have the activity coefficient is given as a negative log value, so you'd have to actually take 10 to the minus the power of this side after you solve for this side to actually get the activity coefficient. We also see that there's a Z again, just like there was in the ionic strength equation. That's the charge of the ion that we're looking at. We have the ionic strength as a factor in activity coefficients. Then we have this alpha value. This alpha value is going to indicate the radius of the hydration sphere of an ion. And those are data points that have a significant amount of error, but are tabulated for us. Notice that most of the activity then is going to be based on this Z squared term. The charge is going to make a much bigger difference in activity, and the ionic strength. We're going to see that down here, this is going to play a pretty minor role in the overall activity coefficient. So the hydration sphere is important, but not nearly as important as these other factors. Nevertheless, we can use tabulated values of those different alphas, and those tabulated values are all on table 10.2 of your text. Pretty much any text will reproduce from the same journal article a long time ago for these same alpha values and tabulated ionic or activity coefficients at different ionic strengths. So some things that I want you to notice is that generally we're going to have the most difference in activity when we are at the bottom of this graph. Notice that up here at the top of the graph we have very few changes in activity. At the bottom we've got about 50% error if we don't use activity, and it's going to get even more drastic as we increase ionic strength. And so if we increase ionic strength to about 0.1, we have a huge decrease when we have things that have a high amount of charge. Again, the charge and the ionic strength are going to make the largest difference. The radius, which is given in this column, is not going to make nearly as much difference. Another way of looking at this graphically is we can look at a couple of different things, potassium, calcium, aluminum, and iron cyanide. And when we look at these different things that all have not that different hydration spheres, we see that potassium is going to be affected very little by the ionic strength, whereas iron cyanate is going to end up being affected drastically. So what are the practicalities for using these activity coefficients? At low ionic strength, or low mu, and for singly charged ions, usually we get pretty small amounts of error from using concentration. That's why we've done it in the past, and that's why a lot of times we'll probably still continue to do that. But practically, at mid to high ionic strength, we need to use activity coefficients. There's a problem though, because when we try to find ionic strength, we really should be using activity as well. So our ionic strength equation really should look like this, where we use activity, and the activity is determined by activity coefficients as well as concentration. But in order for us to find the activity coefficients, we need to have the ionic strength. And so it's actually a circular set of equations. So how can we practically deal with this unsolvable system of equations? So first, we're going to solve for the activity using an estimate of ionic strength. So we might have some idea of what the ionic strength looks like, or we might be able to make some guess, and we can solve for activity based on that. After we do that, we can solve for ionic strength using activity. After we do that, we can repeat again until we get the same ionic strength. So we can repeat over and over every time we should be getting closer to consistent ionic strengths, and eventually we'll have solved using the right ionic strength for activity, and it will give us the same ionic strength back. So it's a little bit tedious, but it works pretty well, especially if you repeat the calculations in Excel, because then you can just alter the ionic strength each time you come out with a new value. In a design experiment, we can actually control this even better because we can use a salt buffer to control ionic strength. So if we're doing experiments that are mostly going to be on the millimolar range, we can use a 0.1 molar buffer of sodium chloride, and then we're going to have that dominate the ionic strength equation, and it's never going to change. That's probably the most practical way of dealing with these things.